Um, Hello, everyone. So this is Srushith. I'm the head of engineering at Confab, and today's session is about serverless beyond Lambda functions. So let's get started. A little bit of introduction about myself. I'm the head of engineering at Confab, a serverless consultant, a co-organizer of one of the largest serverless meetup groups, that is the serverless architecture meetup group in Bangalore, and I'm also a mentor at Girls Script Bangalore. So if you guys are interested in serverless and want to discuss or talk about anything, you can follow me on Twitter, you can follow me on LinkedIn. I'm pretty much active everywhere. I'll be more than happy to talk about serverless. So let's get started. Okay, so I'm pretty sure you guys have already understood from the previous sessions about what is serverless and where it is coming from, what is the evolution and stuff like that. But before I thought I could start, just a brief introduction for people who probably needs or joining now and needs a little bit of intro. Serverless, this is how serverless has evolved over the years, right? So we had physical machines, then we had virtualization that came into picture, then cloud, then came containers, and then serverless. So at each point in time, there is one level of abstraction that has happened, and one level of problem, if you think about it, is taken away from the developer's perspective, and one less thing to be worried about. And with serverless, it is all about the business logic that we write and nothing else. We don't have to manage any infrastructure or any sort of scaling and stuff like that. We don't have to worry about anything. The cloud provider, in this case AWS Lambda, takes care of everything for us. And as an individual developer, our main focus is to just write business logic and solve real world problems. So that is what it is, serverless. And I'm pretty sure most of you already would have explored, or from the previous sessions would have understood what is serverless and things like that. So without getting much deeper into the introduction part, I'll just get started with the topic for the day. So as the topic talks about, it is serverless beyond Lambda functions. So most people perceive that whenever we talk about serverless, it is going to be just Lambda functions, but it is not the case. If you guys have built any small, simple applications or have worked with AWS Lambda in production, you guys will understand that Lambda is just one small, tiny piece. Of course, it takes a lot of, it does a lot of things, but then still, it is just one small, tiny piece. Right? You need various other services to come together and play as a team, like an orchestra, where they all perform some wonderful music for us, for the application to be up and running and like scale automatically and all those things that comes with serverless, right? So this session is not going to talk about what are Lambda functions and what can be done, what are the triggers and what are the event sources and stuff like that, but it is going to be about how we will be leveraging various other services that are also serverless, but then which are very less talked about, or which are less sort of less explored. So that is the thing that we will be focusing on today. And the first service that I would like to talk about is the AWS Step Functions. I don't know how many of you have already used step functions, but this is one of the services that I feel is not very much touched upon when it comes to the serverless world, where people talk about, okay, if you think about it, if you think about the various sessions and the getting started things, you will understand that people talk about Lambdas, there's API gateway, there's DynamoDB, and then how you collaborate or how you integrate all these three services and bring up or build a small simple application, right? And then there's an S3, and then we have IAM and all sorts of things, right? But when you come to real world, there are a few things that we'll have to take care about, right? One of the few things is, so when you build a real world application, it's not just one Lambda function or two Lambda functions or three, right? You have a proper application, you have a proper product where you have numerous Lambda functions. You have a lot of functionality that needs to be done. So if you go by the best practices of Lambda functions, it is about single responsibility principle, right? Each and every Lambda function should do one and only one thing. If you go by the principle, what it states that you have like 50 features that you want to implement, and then there are 50 Lambda functions if you take one Lambda function per feature. But then in real world, it's not the case, right? What happens is you have multiple Lambda functions per feature, So the number of Lambda function goes exponentially the moment your product or your application grows in complexity and more and more features are added to the application, right? So what is the problem? So serverless is very, very simple, very, very easy to get started. There's no problem at all. I mean, I'm pretty sure whoever have just got started with serverless would find it, oh, this is amazing. You just have one create button in the AWS Lambda console. Go there. There's a boilerplate code ready available for you. Then you have a designer where you can simply add an API gateway, and you have a REST endpoint for you, and then done. You have a hello world application, right? It's very, very simple and straightforward to get started with. Absolutely true. But the more and more we dig deeper is where I mean, like any sort of technology, right? It has its own pros and cons, right? With Lambda functions, what I personally feel is the more the product increases, the number of Lambda functions exponentially increases, and then playing all of them together becomes a little tricky. The monitoring, everything becomes a little trickier. So this session is going to touch upon a few aspects of all those things to help you guys build serverless applications and try to leverage all the various other services, not just Lambda API Gateway, but the other services that can help you build really good, amazing serverless applications. Again, Lambdas as such are a wonderful service. I mean, they can scale automatically. We don't have to really configure anything much. I mean, minor configurations like the timeout and then the runtime environment and stuff like that. But as such, there's no heavy configurations that we will be doing when we are building Lambda functions, right? But that's what. When we are building serverless applications, it is not just the Lambda function, but it is all the various other services that come into picture. So let's get started with the first service, that is AWS Step Functions. Now, so what exactly is a step function? I mean, if you guys, for people who have already used it, they would understand that it's sort of a flowchart that helps you orchestrate your application flow, user flow, while building your applications, right? I'll be touching upon a simple example as well. Before I go there, let me just explain you what exactly a step function is. So as I told you, in real world applications, you have numerous Lambda functions, and for one feature, you'll have multiple Lambda functions that are doing their designated purposes, right? So when we have multiple Lambda functions, it becomes really important that as a user flow, you call one Lambda after another, after another, after another, right? There's a user flow that happens. So each and every Lambda function has to be called upon in a specific order. So you have to orchestrate the Lambda function's execution so that the user flow is maintained and you achieve your functionality, right? So there are multiple ways how we can do that. One way is, you can call a Lambda function, let's say Lambda 2 from Lambda 1. So after execution of Lambda 1, we can call Lambda 2. After Lambda 2 executes, we can call Lambda 3. So stuff like that. So we can obviously code for that in our application itself. In our, let's say you use Node or Python, we can use the SDKs to call the second Lambda function or third Lambda function based on the execution. That is one possibility. But imagine, which I will be showing a little complex user flow where, let me just show you that. So this is a simple example, right? Where you have a little complex flow where after one Lambda function, you want to do something else. And based on the response of Lambda 1, you want to execute either Lambda 2 or Lambda 3 and stuff like that. So there's some kind of a conditional execution that you want to achieve with your Lambda functions itself. So with step functions, step functions offer this out of the box for us, wherein so we can orchestrate the Lambda function. Let's say you have 10 Lambda functions and you have a specific user flow. Then what will happen is you can define that as a simple JSON, and AWS will take care of executing that step function so that, there's an order now. You have one Lambda after another, after another, after another. So there's a proper set flowchart, like I showed you, that executes and your user flow is executed. So instead of we hard coding or rather invoking one Lambda after another, we can simply use step functions, which gives us out of the box things. Now so invocation is one part of it, right? There are various other things. So a few of them I've mentioned here. One is the orchestration. So it really helps in orchestrating the Lambda function instead of we in the application code orchestrating for the same. So you're moving out the orchestration logic from the application layer and keeping it one level higher so that the flow doesn't actually really creep into the application logic, right? So that is the orchestration advantage that we get. But then there are multiple other things. The other one is parallel processing. Like I mentioned just before some time, based on the response of the first Lambda function, I want to decide what I want to do. Instead of me actually writing that code, let's say, for example, it's a very simple thing. I don't want to handle at the application level, but rather what I will do is code for it in the step function. And let's say lambda1 returned an array of 3 objects, right? And for each of the object, I want to perform a different, or I want to perform some computation, right? So instead of we handling all sorts of things inside the Lambda function where we write a for loop, and then based on the number of items that we get from the response, we execute the for loop and stuff like that. Instead of all sorts of things, we can simply leverage the parallel processing from step functions. What it does is, based on the response, how many other objects that I get, I will trigger so many Lambda functions in parallel, and for each of them, I will start executing individually. Now, what is happening is, I don't have that for loop in my application, and I don't really care about whether am I getting an array of 1 object or 3 objects or 15 objects, right? All of that logic is extracted to the from an infrastructure point of view. It is extracted to the step functions, and it is no more at the application level. So that is one of the advantages of what we have from parallel processing. And the next one, which I find is it's very useful, is the retry, time wait, and conditional execution. Like I said, based on the response of one, execute the other, and sorts of things. That's the conditional execution, right? And apart from that, we have retry and wait logics also built into step functions. Now let's take a simple example. We have one Lambda function that connects to, what happens is, let's take a simple example. Where we have a simple application where people upload their visiting card, okay? And in the visiting card, we have the address as well, the business card, right? We have the address of the person as well. So what we want to do is, before we update to the database, I want to verify or store the geolocation of that particular address. So I would want to call the Google Maps API or something like that, a third-party API that gives me the lat long and stuff like that. So what will happen? I run some image. I run recognition, which is another AWS service, to understand what is the text that is available on my business card. I'll understand that this is the location. I will call the Google Maps API or any location API and get the latitude and longitude, and store it in my database for further processing. Now, let's say for some reason the Google Maps API is timing out, or you have crossed the rate limit for that particular minute or that second. There's some kind of limits, right, for any API. Now, what will happen is, in the application, what we generally do, we handle such kinds of errors. So after calling the Google Maps API, we would have a try-catch block to ensure that if at all there's any problem, I catch that. I wait for some time in my application to ensure that, because I'm pretty sure my third-party API that I'm consuming is actually very reliable. There should be some reason, some network issue or some rate limit, or for a split second, Google Maps API is down, right? We never know. So stuff like that. So what we'll do, we'll have a retry mechanism in place in our application logic. So after 1 second, just try it out again so that you probably can connect to Google Maps and get me the latitude and longitude. Now, such kinds of retry logics, which really is not at the application level, it is not really dependent on a service that you are building, but from a third-party service or a service that is not probably very reliant or stuff like that, we try retry logic. We write retry logics. So what step functions offers us is, instead of we retrying that as a part of our application logic, we can retry for a specific state. So in step functions, we call states. So we have tasks, we have states. So where each state can be handled, we can have a retry logic for every individual state. And if at all the Lambda function fails for a specific reason, because we are already catching it, right? So we know why it is failing. So we can configure saying that if at all this Lambda function, which is responsible for connecting to Google Maps and getting the latitude and longitude, is failing for a reason for, like, let's say, a rate limit, then wait for a couple of seconds and retry again. So stuff like that is extracted out from the application logic and is written into the step function configuration. Therefore, we don't have to do anything. Everything is taken care of. So that is one is retry. Then that is one simple example of retry. Then we also have another another advantage, that is the time. A lot of times what happens is we have multiple Lambda functions running in parallel, and we want to wait until the previous Lambda has completed, right? For, let's say, for example, we are dependent on a file that is being uploaded into S3, and that processing is being performed by another Lambda function, right? So we really don't know how long that might take. It might take a few seconds extra. So what we can do is, either in our application logic itself, when I'm triggering two Lambda functions parallelly, one Lambda function to upload the file, processed file to S3, and the other function to probably read that from S3 and perform some kind of another operation, right? Instead of me handling that wait inside the Lambda function, instead of me saying time.sleep, like something like that in Python, right, where you wait for a few seconds before you actually start your execution and stuff like that, what we can have is we can have a state in the step function itself which waits for a few seconds. Before I execute my next Lambda function, I'll wait for a few seconds because I want to be 100% sure before I get into the next Lambda function, I want to be sure that the file is available for me, right? So all these kinds of stuff which can be extracted out from the application logic, which we don't really have to code for, can be written into simple JSON in step functions. That is the power of step functions that gives us when we are building a stateful model. Again, one thing that I actually forgot, which I should have started with, is basically Lambda functions are stateless, right? So basically, one Lambda function does not really know the context or the state of another Lambda function, right? With step functions, it gives us the capability to pass the state from one Lambda function to another, because we are now building, it's a state machine where we are trying to build a state machine and try to orchestrate different Lambda functions to work for one single feature or one single user flow. So these are the various features of step functions and trust me, it is very, very simple because it is simple JSON that we have to configure for. And the retry logic, the wait logic, all the things I have told you is a simple JSON configuration that we write, and then it simply gets executed. I mean, AWS takes care of executing those Lambda functions for us. Now, this is just the pointers that I just talked about. It helps in orchestrating the various services for our Lambda functions. I mean, we have multiple Lambdas, we orchestrate it. And then, as I told you, it helps us build stateful services, whereas Lambdas by default or serverless applications by default are stateless, but step functions gives us that capability to build a state inside the application, I mean, for our user flow itself. Now, as I've already mentioned, it has the capability to do parallel processing as well, and easily integrates with various other AWS services. I've been talking about Lambda functions alone, but step function also integrates to various other AWS services as well, that you can trigger from your step function. Instead of using a Lambda function to trigger another service, you can probably use a step function. After the execution, a successful execution of my Lambda function triggered this. So sort of things that can be done with step functions. It's not just about Lambdas. A lot of the retry, time wait, conditional execution, etc., are provided out of the box, and we don't have to code for that. And as I said, it's a simple JSON configuration that we will be doing, nothing much. Now, this is a simple example of, let's say, when we are ordering on Swiggy, or when we are ordering on any food ordering application, right? What happens is a user places an order. The moment we place an order, the restaurant is actually notified saying that here is the order for you. You have to start preparing this item. And once the item is prepared, the user is also notified saying that the item is prepared for us. And then what will happen is the delivery guy is notified. There's a bunch of process or flow that happens, right? So to put it in a simple architecture diagram like this, what it happens. So this is one kind of way of dealing with this application of food ordering. So this is what is called as choreography, right? So there are individual Lambda functions, and there is someone who's taking care of. I mean, they are choreographed to perform a dance, right? So they are choreographed. So each Lambda function has its own responsibility, and they have their own triggers and sort of things. And the moment there is a trigger, the Lambda function executes and goes down, right? So this is what is called as an event bus, where we can trigger various Lambda functions based on the input that is coming in, and the Lambda functions based on the events that is coming in, and the Lambda functions get triggered. So the moment there is an order that is placed, so the user is placing an order via an API that is integrated to a Lambda function, and that triggers an event bus, which is nothing but an event bridge, and a message is pushed to the event bridge. And based on the message that is being pushed, the dedicated Lambda functions picks up those messages and start executing whatever they need to do, right? And once the order is placed, and we have accept order, complete order, various very simple application, right? We have quite a few flows. So this is how it would work if it is an choreography. This is one way of doing things. Now, the problem of doing this, absolutely, this is a wonderful architecture, this is a wonderful way of doing it, right? But what is the issue, or what is the problem with doing like this? I mean, the advantages, what are the advantages? Let's start with that. The advantage is that each and every Lambda function is independent, and they can scale, and they can be configured, and they can be changed as such. It's not really tied. They are very much decoupled, right? So they can be changed. They can be it's like a building block, right? Where you have Lego pieces. You have one Lego piece that you want to fit into the architecture. It can simply come in, and based on the events that is happening, it can come up, execute it, and go away, right? So that is what happens with this kind of architecture, where you have individual pieces that are very much decoupled, and there's a very much scope of a very good scope of reusability, where, let's say, for example, notify user is not just for when an order is placed, but let's say, for example, I have a promotional offer, something like that. So all those kinds of things also can be done by the same Lambda function, and can be triggered. So that is the advantage of this kind of an architecture, where we can reuse multiple things, and they are pretty much decoupled, because it's all event based in it, like in any application, right? Now, this is another way of doing it. That is the step function way, which is called as the orchestration, right? So what we do here is we have specified user flow that talks about after notifying the restaurant. Then I have defined, saying that after the notifying, I have to wait for the restaurant to accept it. Then once the restaurant, as I told you, this is the conditional execution that I was talking about. If the restaurant has accepted it, then notify the user, wait for the restaurant to deliver, and then complete the order. If at all the restaurant is not accepting for whatever reason, let's say, for example, suddenly it started raining and all sorts of things, right? So we can directly cancel the order. And if at all there's some problem while delivering or while preparing the order, we can have a catch block. So as I told you, we can have retry mechanisms. And apart from that, I can have a constant try catch block sort of a thing, where I can catch for any error in this flow, and I can call the cancel order and stuff like that. So all of these are also possible with step functions. So this is another example of how we can architect such kind of an applications. One is the choreography way, the other one is the orchestration way. Now, what is the cons of the previous approach? In this approach, it becomes it is sort of difficult to monitor it, because there are so many Lambda functions and they're sort of very much decoupled, right? So the monitoring and the flow of how the events are passed from one to another is sort of debugging, if you think about it, becomes a little trickier, because we don't know where exactly it is failing. So it becomes a little trickier when it comes to so much of decoupling. But whereas here in step functions, as I told you, I know exactly where it is failing, and I actually can have a catch block for a specific state, saying that if at all, for whatever reason, the complete order failed, I can have a catch state to do something else and stuff like that. So this is the advantage of writing with step functions. The other advantage is, because we are configuring this as a JSON, it becomes as a part of our infrastructure as code, right? It goes to our source control, and it starts being a part of our Git. So anybody who's trying to look at this application, look at this user flow, they can clearly understand what is happening where and what is failing where. So that is one of the really good advantages that I feel about step functions. So various use cases of step functions is batch processing, automated tasks, state management, as I told you, where you can maintain a state while for a one particular user flow, and we of course have application orchestration, which we talked about. So if you ask me, step functions are really wonderful, and they help us in serverless applications. As I told you, orchestration is one of the challenging things, and maintaining state, of course, is another challenging thing. And step functions actually help us solve that problem. So that is about step functions. The next one we have is AWS Appsync. As I told you, the topic for today is about not just Lambda functions, but then how we can build serverless applications itself, right? AWS Appsync is a managed GraphQL service from AWS, which helps us write GraphQL APIs. As simple as that. I don't know how many of you guys have built GraphQL APIs, but on AWS, it's Appsync, the service that will be used. For people who have not used or worked on GraphQL, here's a very basic introduction. I don't know how, I think most of you guys have already seen this image, right? So GraphQL helps us, I mean, it gives the power to the client to ask for what they want. In a REST API, it's as simple as your api.com/a burger. I want a burger, as simple as that, right? And the server, or in our application, the Lambda function will return a burger. Now, what if I want customization on top of that? I don't, like I show, like in this example, where I want a burger, but I only want the bun, the patty, and then the bun, and then lettuce. So it has that, it gives the capability for the client to actually ask for what they want. Whereas in REST API, it's like, okay, you want this, that's all. We don't, the client doesn't really have the capability to ask, okay, I only want these parts of the response, right? So GraphQL is very much picking up, I mean, a lot of amazing applications and a lot of amazing services that we can build GraphQL APIs for, and AppSync is one among them. What are the advantages of using AppSync? Highly scalable GraphQL APIs. So AppSync is again a serverless service. So of course, like you all know, when it comes to serverless, what are the advantages, right? The basic advantage. So what can you term when can you term a service as serverless? One thing is you don't have to take care of or manage the infrastructure. The second one is you are charged only for how much you consume, pay as you go, the true pay as you go model. And then we have scalability. So we as the application developers don't really care about the scaling of the application, right? So these are the various characteristics or attributes, if you ask me, which can be classified for calling a service a serverless. So with AppSync, we can build highly scalable GraphQL APIs. We don't have to manage anything, just like API, right? We don't have to manage anything. Everything is taken care by AWS itself. And the other advantage of building GraphQL APIs, and especially with AppSync, is it gives us out-of-the-box capability for WebSockets called as subscriptions. So in GraphQL, we have three kinds of things. One is queries, mutations, and subscriptions. Queries are like the GET APIs of the REST world. Mutations are like the other operations, like update, delete, and stuff like that. Create, right? So with with GraphQL, it is queries, mutations, and subscriptions. So subscriptions is like real-time data push back from the server to the application, and we use subscriptions for doing the same. And with AppSync and GraphQL from AWS, it comes out of the box. We can simply write a subscription or define a subscription and integrate it with the Lambda function, and everything is taken care of. So that is with the subscriptions. The next very important feature or thing that that is very underrated sometimes is the fine-grained access control. See, with REST APIs, what happens is we have an authenticated API, you have an access token, or you're logged into Cognito, then you can access the API. Simple and fine, right? That's wonderful, right? If I want to access the API, I have to be authenticated. Wonderful. But think of a scenario where I want the API to be open, but if you want to access some really sensitive information, then you either have to be authenticated or you probably have to be the owner of that particular record in the database and stuff like that, right? A simple example. You have a blogging website and you have a number of blogs that is being displayed, right? And you don't want and it's an open blog. So anybody can come to the blogging website and they can simply look at the blogs, read about it and stuff like that. But apart from that, let's say, for example, every blog author has an email ID. So the email ID we don't want to expose to our non-logged in users for whatever reason, right? What we can do is with AppSync, we can have fine-grained access control saying that not at the API level where based on the authentication, I will return the response. It's not going to be that. Rather, what I can do is I'll return the response. But if you're asking for something, as I told you, GraphQL is all about you asking me what you want. And if you're asking me for some really sensitive information, you better be authenticated. So stuff like that, we have single API, and Appsync gives us the flexibility to have authentication, not at the API level, but at every field level. So if I want to return the email ID, I should be authenticated. So stuff like that, this is a fine-grained access control, which I personally feel is really amazing, so that you don't have to build two sorts of APIs. One is the public API where we are not returning the email address, another authenticated API where we are returning the email address as well. Instead of doing it two times, we can leverage the fine-grained access control of Appsync itself and return only the necessary information for people who have the right access. So it's, as I've already mentioned, it's a managed GraphQL service that can scale to millions with ease. Easy integration with DynamoDB and RDS. Again, for people who have not used Appsync or GraphQL, so what happens in Appsync is, generally what happens with API gateway. We have an API gateway, we have a Lambda function, then we have a DynamoDB. So we trigger the Lambda function to get some data from the database. Let's say, for example, DynamoDB or an RDS instance and stuff like that. Right? Most rather than not, what happens is we use the Lambda function just to transform the input or transform the output. Correct? Most of the times, they say that, okay, get me this user details. What we will do, we'll go to the database for this user ID or username or email ID or whatever it is, get the data and return the response. Simple, right? We write a Lambda function for that. Instead, API Gateway also has this capability where we can directly connect to DynamoDB instead of having a Lambda function in the place for just transforming or transporting the request from one service to another. And with Appsync, it is even better because we can actually connect to an RDS instance as well, like an Aurora Serverless instance, where we can write some simple SQL queries, and in Appsync, using VTL as resolvers, we can write simple code in VTL to connect to different data sources and get the data without writing a Lambda function. If you ask me, the best serverless application is an application that does not have a Lambda function. Right? We have to write as much less code as possible. Correct? I mean, the whole point of serverless is to move away the infrastructure. I mean, we don't have to take care of infrastructure, just target the business logic. And I'm telling you, if we can achieve something that can be written without the Lambda function itself, that's an even wonderful application. Like I just mentioned, we can directly connect Appsync to a DynamoDB or an RDS instance. The same thing can actually happen with API Gateway as well. You guys should explore that. It's incredibly easy to build WebSockets, as I said, using subscriptions. Then we have fine-grained access control, and we also have Cognito-based group authentication and authorization mechanisms that is available for Appsync. The next service that I would like to touch upon is the Aurora Serverless. I think there was a session in the morning as well about Aurora Serverless. So what is Aurora Serverless? So it is a SQL database, if you want. Like we have an RDS, right? We have the serverless mode in RDS, where instead of having a normal RDS where there's limitation on the size, limitation on the number of connections and stuff like that, AWS came up saying that, until a few years ago, one of the blocking points or for building serverless applications was Lambdas can scale beautifully. There's no problem. But my database, it is an RDS instance. There is a limit on the number of connections that can concurrently happen to my RDS instance, correct? Now, my Lambda functions can scale to infinite, but my database cannot. So it's sort of a bottleneck or sort of a limitation sometimes, because so now you have I generally use this terminology where you have a Ferrari body and a normal, let's say a four-wheel vehicle engine, right? You have really good, powerful body available for you, but you don't have the enough capability to run faster, right? So then came Aurora Serverless. So the database itself can scale automatically without we configuring for anything. I mean, of course, see, there's a star with everything that I talk about, right? You still have to make some configurations, but just to talk in the general terms, we don't have to really worry about the connection management that is happening or the storage capacity that the DP is having. All sorts of things are taken care by AWS, and we have an on-demand auto-scaling DB for us, and it is still a SQL, MySQL database, or we can have Postgres, all sorts of things, right? We don't necessarily have to shift to DynamoDB. In a couple of years back, most of the people were really worried about saying that, I really love Lambdas, but the problem is my database cannot scale. And the scalable database that I know of is DynamoDB. But that's a NoSQL database. I cannot convert my relational data to NoSQL just because I want to leverage AWS Lambda, right? Now, that is when we have Aurora Serverless coming into picture, and that is, it automatically scales and we don't really have to worry about it. Now, use of data API, no problem of connection pool. This is the another really wonderful advantage of Aurora Serverless, is that we don't need to have any connections. I mean, we have something called as data API, where we execute SQL queries via an API itself. We don't necessarily connect to the database and manage those connections. We don't do that. We use the data API, and AWS takes care of using the data API. AWS takes care of managing the connections, and based on the number of connections that is happening via the data API, the Aurora Serverless scales as and when it feels like, and it can scale down as well. Obviously, it's a serverless database after all, and then it's of course cost effective because I don't have to necessarily touch upon this, right? Because your database is scaling as your requests are coming in, as the load is increasing, and then it automatically comes down. So you're charged based on how many ACUs, we call it as ACUs in Aurora Serverless, where based on a number of ACUs that is being consumed at a given point in time, we actually are charged. Instead of always having a really large instance, it is very much elastic. It constantly keeps up and down based on the request that is coming in. So we have the Amazon Aurora Serverless is an on-demand auto-scaling configuration, as I told, easy querying with data API. We don't necessarily have to connect to the database. We can use the data API to run SQL commands, and that connects to the database. Auto-scaling with no configuration, as I told you, no problem of connection, pooling, or management. It's very cost-effective because it's going to be per hour building, and that per hour also is based on the number of ACU units, Aurora capacity units that we are consuming. So it is going to be cost-effective based on the load that is happening, highly available storage, and this is best suited for variable workloads. Like any serverless application, you have very unpredictable or variable workload, then this is the best. And just to continue on the advantages, no CPU credits to monitor, no commitment to a particular availability zone. So Amazon Aurora takes care of that. And then the various things that I have talked about, no instances to manage. It's a serverless thing, of course. And encryption at rest is enabled by default, and no need to manually suspend, resume, or scale database. Everything is taken care by Amazon itself. So the various use cases for the Amazon serverless that I could think of is when we have periodic jobs or reports that we want to run daily, weekly, it's not something that I want to run 24/7, but something that comes up and comes down based on every daily or some kind of a schedule, right? Stuff like that. Then we have dev test environments. This is one of the really, okay. With Aurora Serverless, there's one more thing that I missed to talk about. Is there's something called as DB Autopause. What exactly is DB Autopause? So whenever there's no connection or any activity on the database goes to sleep. So the database actually sleeps, and as long as it is sleeping, we are not paying anything to AWS. The true serverless mode, right? Because we are not consuming anything, so we don't pay anything for consuming the database service. Now, where is this advantage? So one thing that you guys have to remember is this DB Autopause is wonderful, but the problem is the startup time is close to 30 seconds. So let's say, for example, there is no activity on the DB for, let's say, 10, 15 minutes or for half an hour. This is a configurable time. Let's say there's no activity for 30 minutes, the database goes to sleep, and there's a new request that comes in. It's not like a Lambda function that is just instantaneous, that comes up, executes, and goes. This is a database, right? So it takes a little bit of a time to come up, and based on my usage, it's close to 30 seconds it takes. And for production loads, it's not acceptable, right? You cannot ask your user to wait for 30 seconds for your application to be up and running. So that is why it's very much suited for dev test environments. But then we enable pause only for dev test environments. For prod, we don't enable any pause time. So either there is activity or not, the database keeps running. So there's no problem of cold starts, and there's no problem of 30-second limit. But the advantage is your dev and test environments are not being charged so much. We are not running it 24/7, right? It is only, and it's dev test environment anyway. People, the developers or the testers can wait for 30 seconds for the database to come up and running. So it is very much suited for dev test environment to enable the DB auto pause, and whereas for the production, just leave it as is, and you have the advantage of the scaling, the pricing, and everything. So automatic adjusting to load capacity. So the last service that I want to touch upon is the RDS Proxy. Now, for people who are traditional to RDS and they really love Lambdas, but they want to bring both together, right? Aurora Serverless is one option, but what happens is a complete different variant of RDS. But you have an RDS instance already present. You want to have it, excuse me, have it as a part of your serverless application, right? What are the limitations? I just talked about the number of connections that can happen to my database instance is limited, but for my Lambda functions, no limit. They can constantly scale. So what happens is you have an RDS instance, and then we have the client applications. We have RDS proxy that sits between the client applications and the RDS database. So the RDS proxy so we don't connect to the database directly. We connect to RDS proxy, and proxy connects to RDS database. So the proxy takes care of managing the connections and reusing the connections that is already available. So what will happen is the bottleneck that we had down the stream, because of my APIs can scale, my Lambdas can scale, but my database cannot scale. So now what will happen is we are trying to move away from that bottleneck and use RDS proxy as a barrier, so that I'm not overwhelming my RDS instance, but my RDS proxy takes care of managing all the connections for me before it can connect to RDS instance. So that is about RDS proxy. It is the RDS proxy is fully managed, highly available database. The scale, as I talked about, right? Generally, RDS has a scaling limit based on the number of active connections for a given point in time. So that is now moved out of RDS, and RDS proxy takes care of that. We have improved database efficiency, application scalability, and security, because now from the application, we are not connecting to the database. Actually, we're connecting to RDS proxy. So we have one more layer of shield for us from the data itself. And then the best part is combining the best of both worlds. One is RDS and serverless itself. So now we have a proper application that can scale to what my serverless is, my Lambda functions are capable of, and everything downline can help me, or there are no bottlenecks or stuff like that that can slow down my application. So that is pretty much about the session today. Thank you so much for everybody who have attended. And once again, this is Srushith. You can connect with me on Twitter or LinkedIn. I'll be more than happy to discuss about serverless.